our approach to do linear algebra. This is in Professor Vijay K's lectures. Okay. Okay, let me reduce the. Okay. Okay, so let us start. Okay, so the basic setup is the following. K. So basic notation, we keep this fixed for the entire set of talks. So K will always denote a field. Okay, you can take this to be R or C, if that makes you comfortable. You can take it even to be Q or some other field or finite field, whatever you like for the moment. It becomes important what that field is at some point. So we will take note of that as and when we require, as and when that is needed. For hello?
Sir?
Am I okay? I saw something on the screen. I'm audible, right?
Yes, sir. Yes, sir. Yes,
okay.
Sir.
Okay. Right. So finite dimensional vector space over K, over this field K. So you can, if K is R, e.g., so for example, you can take K equal to R and V is equal to Rn, right? Or let me write Rd here, because I'm going to put D to be, I'm going to fix D to be the dimension of V over K. Okay, and in linear algebra, the very basic theorems about linear algebra concern, so let T be a linear transformation from V to V. Right? Or that is, what that means is, in other words, more technical words, K linear map. That's what we call it, right? From V to V. So this means that, so let's write it out what all this means. T respects multiplication and addition. Sorry, T respects addition in the vector space. So you have something like this. This is that fact that T respects addition and T respects scalar multiplication. So this is lambda times TV, and this should, of course, hold for all V and V prime in V, and for all scalars lambda. So by a scalar, we just mean an element of the field. Okay. So of course, the word scalar is maybe has physics, originates in physics, and usually, if you are told in school that scalars have no direction, maybe vectors have direction, etc. That is all, as we grow older, we realize that's all something that you tell children. It just means that it's a element of the underlying field. That's all it means for us. We don't need to worry about whether it has direction or whether it doesn't have direction. All that is context dependent, and we are not worried about that. Okay, so T, you can, as you know very well, T you can represent by a Okay, no, that's not good. Let me introduce some notation. So by M sub D K, I mean D cross D matrices with entries in K. So let me call it over K. Okay. Now, as you know, this is a ring with identity. Okay. It is not commutative. It is not commutative because we know matrix multiplication is not commutative if D is bigger than or equal to 2, or for D bigger than or equal to 2, doesn't matter. So is this all right? This is matrix multiplication. You can add two matrices of the same size, both D by D, and you can multiply these, and the multiplication is associative and distributes over the addition, etc. And there is an identity. It satisfies the axioms of a ring, but it is not commutative because we know matrix multiplication is not commutative. Okay. Now, the thing to observe is that, okay, let me introduce one more notation. By this, we mean K linear, set of K linear maps, let me say. So when I say D by D matrices over K, I mean set of those, right? So here, let me write set of, okay. Since I've not written it here, I will not write it here either. So I'll just say K linear maps. It is the set of K linear maps from V to V. Okay. Now, this is also a ring. This is also a ring with identity. Okay, I can add two linear transformations or K linear maps, and I get another linear transformation. And if I multiply a linear transformation by a scalar, lambda, that too is, so for example, lambda times t, if t is a linear transformation and lambda is a scalar, its action on V is defined as lambda times tv. So this is the definition of, so this defines lambda t. Okay, so this is, well, okay. That shows this is a vector space. This is also a ring. You can composition. So T1 composed with T2 is nothing but T1. You have first apply T2, and then, so this defines the multiplication T1 with T2. Okay, or you can just write it as T1, T2. You can forget this circle. Okay, so this is also a ring, and this composition is also not commutative. And in fact, these two rings are isomorphic. So end KV is isomorphic as rings to MDK. So this is as rings. This means isomorphic as rings, but this is a non-canonical one. Since this involves a choice of a basis. Or basis for me. So what I'm trying to refer to you is the following, that as we know, you've learned that if you have a linear transformation, you can associate a matrix with it, right? In general, if you have a linear transformation from V to W, and then V has some dimension, W has some dimension, you can associate a matrix of, a rectangular matrix depending on the dimensions of V and W. Here, we have a linear transformation from V to B. So what we get is a D cross D matrix, right? So I will just give you an example here. So, you can think of this T as a matrix, but that is coordinate dependent in the sense that it depends on the choice of a basis for V. Okay, so let me give an example, but before that, perhaps I should stop here and ask you if you have any questions. Are you comfortable with this level of abstraction, or is this too abstract, or is this fine?
It's fine, sir.
It's fine. Very good.
Yes, sir.
Okay. Okay, let's do an example. I'm going to go to a different color. By the way, I'll share all these notes, so you don't need to worry about. If you want to take notes, you're welcome. But I'm going to share these notes anyway. So if that helps you, relieves you of the burden of writing down as we are doing, and you want to listen, that'll be fine. Okay. So let's take our field to be the real numbers. Okay, and let's take V to be, okay, all polynomials in X. So X is some indeterminate, so this is some indeterminate, some variable or indeterminate. Okay. With coefficients over R and of degree less than or equal to 3, let's say. Now, just 3 is just an example. So in our case, what is D? Can somebody please tell me? D, recall, this was the dimension of V over K. Just to make sure that we are understanding, can you tell me what D is in this case? Can somebody please tell me what D is?
4.
Very good, 4. And what's a basis for this vector space? What could be a choice of a basis?
1x x square.
Very good. Is it anomaly?
Yes, yes.
Okay. Okay. So a basis, choice of a basis. Would be a natural choice of basis, you might say. Of course, this is not the only basis. You could have taken 1 plus x, 1 minus x. I mean, you could, but this, I mean, most people would choose this, I guess, right, if they were asked for a basis of this. Okay. Now, let us, so I'm going to define T to be the derivative map, right? So this is the derivation by x. So if I take a polynomial of degree 3 and take its derivative, it's going to be a polynomial of, I mean, a degree at most 3, and I take its derivative, it's going to be also, in fact, its degree comes down, as we know. So it's also going to be of degree less than or equal to 3. Okay. So can somebody tell me so what is the matrix of T with respect to, so let's call this B. With respect to B, yes. Okay. Now, this involves conventions. Okay. What should be the size of this matrix? It's a D by D matrix, and D is 4. So it's a 4 by 4 matrix. Can somebody please tell me what this matrix is? Using some conventions. Use your own conventions. I'm fine with any conventions, any convention that you want to use. Somebody maybe other than Annamalai. I know Annamalai would know this. What would be the matrix of T?
His first column is 0.
First column is 0. Okay. And may I ask why is that?
Because derivative of one derivative is 0. Derivative 1 is 0. And if we extend in the, according to elements of 1x, x square, x cube, that will be 0.
Very good.
0
Excellent.
into 1.
Excellent.
0
Okay.
square.
Very good. Okay. Right. What's the second column?
that will be 1, 0, 0, 0.
Very good. Okay. And maybe you could explain why that is so also.
Yes, sir. So derivative of x is 1,
Mhm.
and we can write 1 as such, 1 into 1 plus 0 into x and 0 into x square, 0 into x cube.
Excellent.
In terms
Excellent.
of
Very
this.
good. Very good. I'm so happy that this is all something that you know very well. Very good. And please tell me the second and third column as well. Third and fourth columns as well. 0,
0,
2,
0, 2,
0,
0,
0,
0.
because when I take the derivative of x square, I get 2x, which is just
Yes, sir.
twice x and 0 elsewhere. Okay. And then this one.
Yes, sir. 0, 0, 3, 0.
Very good. Excellent. Okay. I'm so happy. Okay. So far we are here, right? This is our example. Okay. So now what is new for us? So this is all something you know. Okay. And I'm happy that this is looks like you're all comfortable with this. Good. Okay. Now let's get back to our theory. So I'll change color. I'll go back to black. Okay. So here is the basic observation that underlies everything that we are going to do. Okay. So we are going to fix, so what do we have here? We have a field such as this. In this example, it was R. We have a vector space. In this example, it was all polynomials of degree at most 3. And we have a linear transformation, which in this case was the derivation by x. Okay. But it could be some other linear transformation, right? Arbitrary linear transformation. So we have this. Now what we are going to do is, so given K, right, the field V, right, and T as above, right? Vector space, you have a finite dimensional vector space, D-dimensional, say, and you have a linear transformation T from V to V. Given these, we can consider, and this is where the rings theory starts getting applied. We can consider V to be a KT module. Okay. And this is a polynomial ring in one variable over T. Okay. So let me not say over T, but in T, which means it consists of all polynomials in T with coefficients in K. So with coefficients in K. Okay, and how are we going to do this? Of course, so how do you make a module? I mean, there are axioms for a module, but what a module, I mean, very big, how to say, saying it a little, I wouldn't say imprecisely, saying it a little loosely, perhaps, is what you have is when you have a module, is that you have some kind of a group, maybe even a vector space, like we have a vector space here, namely V, and you have a ring, and you have elements of the ring act on the vector space, right? And what are the elements here? I know how K already acts. Elements of K already act on V by scalar multiplication. All I have to tell you is how this thing T is going to act. Okay. So, and here is the key thing. So I'm going to put it in a different color by letting this T act as the small t, the variable, acts as capital T. So does this make sense? If you this is a very important thing. So if you have some doubt, you should ask me right now. Of course, later also you are welcome to ask. But if this is not clear, then it's not a bad idea to ask your doubt right away and not wait until later. So for example, if you have something like, so let's go back to this example. So, okay, let me go back to this blue example. As above, here. This. So let's just take this. So for example, if I take here 1 plus 5t square plus 7t power 2022. Suppose I take that, right? How will it act on, how will this act on some, so let me give you a polynomial. So 3 plus 5x plus 9x cubed. Okay, let's put some real number in. So instead of 9, let me put there pi, just to make it. It looks odd, but that's pi is this ratio of the circumference of a circle to its diameter. Okay, can you tell me what this is? Can somebody say what this is? How do we do this? Step by step. So this is the element of the ring. K is R, and so therefore this is a polynomial in T. This is a polynomial which from the vector space. So here the ring also consists of polynomials. The vector space also consists of polynomials, but that should not be that
3 plus 5x plus 5x cube.
3 plus
5x
plus 5x
plus 5x cube.
plus pi x cubed. Very good. That is why are you saying that? I see what you're saying, but let's hear it from you.
So you are saying that small t is behaving like capital T. So
Yeah.
it's a transformation. So we are doing normal multiplication and consider small t as capital T. That's all.
That's all. Right. Exactly. So yeah.
Then 5 times
5 times
t squared means composition of T3. I think T differentiation 2 times we have to differentiate, it's 0 plus 5 into 0 plus 3. I'm sorry, 6x, 6 pi x.
Okay, so 3 times 2 times pi
Into x.
into x. Very good.
Plus
Plus
7 into 0.
Very good. Excellent. That's all, right? The reason is this t acts like capital T, right? And what does t act as? T acts as just differentiation. So t square acts as differentiating twice, right? And t to the power 2022 acts as differentiating 2022 times. But if I'm going to take a polynomial of degree 3 and differentiate it 4 times, already it's going to be 0, right? So here you can see that this t to the power 2022 is just going to act as 0. Right? This t square is the second derivative. It's taking derivative and then its derivative, which is second derivative. So on 3 it is 0. Already the first derivative is 0 on 3. Here, first time I take the derivative, I get 5. The second time it's 0. Here only it is going to act in a non-zero way. And what you get is pi is of course constant. It comes out. And then this 5 is this 5 here. This I hope you can see my cursor. This 5 is this 5 here. That's what I've written here. And I take the second derivative of this pi is constant. And the first time I take, I get 3x square. And the second time I take it, this 3 and pi will stay as they are, x square as derivative 2x. And that's what I have. Okay, and whatever it is, right? So then you can write it out. Okay, let's just do it. This is 3 plus whatever this is, 5 plus what is that? 6 into 30 pi x plus pi x cubed. Right, that's it. Okay, is this clear? Okay. Let me go to the next page. Okay. Now you see, the thing is, this is a PID. Now let's go back to this. So what we want to do is KT is a PID, right? And what is a PID? Can somebody please tell me?
All the ideals have generators.
No, yeah, okay. But before we get there, PID, what does that stand for?
Principal ideal domain.
Principal ideal domain. And when do we call something a principal ideal domain?
All the ideals have generators. All the ideals are principal ideals.
What does principal mean?
It should have a generator.
Okay, more. You're right.
Generated by
Let
a
me say,
single element.
generated by a single element. Okay. See, a ideal in any ring will have generators, right? It may be generated by finitely or infinitely many elements. But you're right. That's what you meant, I guess. But what you so every okay. But before we get there, there are other conditions. It's a principal ideal domain, right? So the conditions are, it's a, so let's, what does this mean? It's a commutative ring with identity. Okay, that's the first condition. Second condition is that it's an integral domain. Right, which means no non-zero devices. Or no zero devices, sorry. No zero devices. Okay, and it means that it is every ideal is principal. Every ideal is principal. That is generated by a single element. Okay, is this clear? Okay. What are do you know that KT is a PID? Can somebody answer that? I'm claiming that KT is a PID. Are you familiar with that fact? That's the question. I can't see your faces, so I need feedback to proceed. So if you're not comfortable, that's okay. Just say it and we can get comfortable with it. I can explain. But it's possible that you know it very well, and maybe I'm asking a rather stupid question. Maybe I'm insulting you by asking this question. If so, you can tell me that also.
It is PID.
It's okay. You know, anomaly, you know that it is a PID. Okay. You know how to prove that.
Yeah, if you take any non-zero ideal, if you take zero ideal, that is trivial, it is generated by zero. And if you take any non-zero ideal, we pick the non-zero polynomial. And then you have to collect, you pick the minimum polynomial, minimum degree polynomial in that. That minimal polynomial generate the ideal. We can prove this is Euclidean domain using the map degree of the degree function. We can, every Euclidean domain is PID and the pole is PID.
Right. Very good. Very good. Excellent. Okay. So is there anyone who's not comfortable with what Anomaly just said? Okay, I'll just recall very quickly the proof that I'll just write down what he said. Okay, but this is very important. So if there is something here that is not clear, you should definitely ask. Okay, so the point here is that there is a division algorithm here. Okay, let me ask you another question. What are other examples of PIDs?
Set of integers is PID.
Yeah, ring of integers is PID. Very good. Okay, KT is PID. Any other example that you know of a PID? Or an example of a ring which is not a PID, maybe an integral domain which is not a PID. What would be an example?
Is it up?
Yes, Annamalai, you were starting to say something.
Yeah, polynomial over Z.
Polynomial ring over Z. Okay.
Yeah. That is not PID.
That's not PID. Right. Okay. Why wouldn't that be a PID?
If you take the polynomial, the ideal generated by 2, x or any prime, x, that should be an ideal, but it's generated by 2 element, 2 and
okay.
x.
Why prime, x?
I can take any element, but I take this should be a maximum ideal. That's
why. Okay. 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 Very good. Some other ring which is not a PID.
Maybe the set of square root of 1 minus 19, like that. You take that type of complicated.
Yeah, so there are, okay, maybe I don't know if Anirban, Professor Anirban is going to do any of that. There is this subject of number theory, which deals with where if you attach an algebraic number to rationals, right? What you get is a PID or not. Okay, so there are number theory. There is a lot of concern with that question. Okay, not getting into that direction. So if I take polynomial ring in 2 variables, for example, k comma, let's say k, t comma u, let's say t and u are 2 variables, that will not be a PID because the ideal generated by t comma u, both of them, there is no way you can generate it by a single element. Okay, I mean that may require some proof, but at least intuitively, if you try, if I'm going to have t comma u, I'm not going to get it with you cannot generate that ideal by with a single generator. Okay, right. Okay, so there are PID is very special. Okay, the basic examples are rings of integers and this polynomial ring in one variable. And there are number theory, other examples of PIDs, but even those, one must say that those are not very common. When you attach things, algebraic numbers, often is it's the ring that you get is quite it's not a PID. Anyway, so Annamalai mentioned the notion of Euclidean domain. Let me not introduce all that formalism here, but what is important, but without introducing the formalism, let me say what is really underlying this. So it's this division algorithm. So let me say it, given f not equal to 0. So in KT, so I am given a polynomial f, right? I'm going to divide by f, and so, and you give me and any g in KT. So the condition on f is that it is non-zero because I'm going to divide by f. There is no condition on g at all. Any g whatsoever, we have elements, unique elements Q and R in KT with degree of R less than the degree of F, such that, so we write it like this. I've chosen Q and R because Q is the quotient when I divide by G, and R is the remainder when I divide by, when I rewind by, I'm writing this wrong. I'm dividing G by F. G is equal to QF or FQ, doesn't matter, plus R. Right? So this is the basic fact. And you do this just by long division. I just keep dividing until I get, if F starts with T power 3 and G has T power 10 in it, I keep dividing that G until the power of G, the highest degree, comes down below F. And then I'm not able to divide. It's just that, this is just a formalization of that procedure. And this is what you get. And let's note here that so R could be 0. So this could be, R could be 0 here. In fact, degree of 0, what do you think degree of 0 should be? Oh, degree of a constant, if I take the polynomial, which is just, say, K is R, that is a ring of the field of real numbers. And if I just take the constant polynomial 3, for example, what is its degree? What's the degree of a constant polynomials?
0.
Very good. But what is the degree of 0 itself?
So you cannot define, I think.
No, see, you cannot leave it undefined because you are going to you somehow R could be 0, so you sort of have to capture it by this. So you can either put -1 and sometimes minus infinity, etc. Right?
Okay, sir.
So this is some convention, okay, for the moment.
Okay, sir.
Right? In fact, minus infinity may be a better convention. -1 sometimes is a good convention. For now, let's not worry too much. The reason why minus infinity is a better convention than -1 is because if I'm going to, because of the following convention, following thing, right? What will be degree of F times G? Of course, F and G have been used above. Let me use something else. Let's say H and K, J, L. Okay. So H and L are polynomials with coefficients in a field, in the underlying field K. So what will this be? What will be the degree of the product? Maybe I'm asking too many stupid questions. It's going to be the degree of H plus the degree of L, right? Now, what if H is 0? This side becomes the degree of 0. This side becomes degree of H is 0. Degree of H is degree of 0. Here you have something. So you want this degree of 0 to be degree of 0 plus degree of L. And this degree of L could be anything, right? So the correct convention is this minus infinity. Because when I put minus infinity plus any finite thing, that is going to be, or minus infinity itself, it's still going to be minus infinity. So this motivates that I should choose my degree 0 to be minus infinity. Okay. Anyway,
degree of the highest power. That's why we choose minus infinity.
That doesn't quite do it, right? I mean, what is the highest power? I mean, it becomes philosophical. What do we mean by highest power, etc.? So, but if you choose minus infinity, then you can keep this. You can still keep this. You can write degree of h times L is equal to degree of h plus degree of L without any saying h is non-zero, etc. Okay. So this is that okay, Annamalai?
Yes, yes. Yes.
Okay. Yeah. Right. So, right. Okay. So this is the division algorithm, and this is the thing that drives everything, right? So, for example, let's quickly prove the thing that so KT is a PID. Okay, here is a proof. I mean, I'm not going to prove that it's an integral domain. That's sort of obvious. In fact, we have used it here. I mean, the degree will add. Okay. I'm only going to prove the part that any ideal is principal. And as Annamalai said, let I be an ideal in KT. If I equal to 0, then of course I is generated by 0, the element 0, right? We are done. Okay. Now, so let I not be 0. So it's a non-zero ideal. Okay. Then we can choose, because it's non-zero, we can choose, let me call it F, to be F non-zero in I. Okay. Now, what I further do is, we choose this F to be of non-zero, it's a non-zero element, be of minimum possible degree. Okay. And further, and say the degree was 3 or something, and it starts off by something times t cubed, etc. Now, that something, let's say it's alpha times t cubed and alpha is non-zero, I can multiply F by 1 over alpha, and the resulting product is still going to be in I, because I is closed under multiplication. If I take an element of I and multiply it by something in the ring, it's still going to be in I. So if I multiply this alpha t cubed plus dot 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 by 1 over alpha, I get t, that thing is also going to be in I. So and that will be monic, that is its leading coefficient will be 1. So further we may choose this F to be of minimum possible degree and monic, meaning the leading coefficient is 1. Okay. So let's do that. Okay, now we claim, the claim, here is the important claim. I claim this I is actually generated by F. Okay, this is the claim. Now this, okay, for the proof of this part is clear, right? That F is in I, therefore the ideal generated by F, which means any multiple of F. That is also going to be in I because I is an ideal. Okay, so let's do this part. So I take, let G be in I. Okay, now what do I do? And here is the thing. I apply this division algorithm. G could be 0, but F is non-zero because F I've chosen to be non-zero, right? So by division algorithm, it's indeed the division algorithm that drives everything. By the division algorithm, write G is equal to quotient. When I divide G by F, I have a quotient and I have a remainder. Not remainder, but remainder. Okay. Now observe R is equal to, if I send this QF to the other side, I have G minus Q times F. Okay. Now both these are, G is in I by choice, F is in I, right, by choice. Again, we've chosen F to be in I, and Q times F is also going to be in I, and I is an ideal, so this difference is also going to be in I. Okay. Observe this. But degree of R was less than the degree of F. And F was of minimal degree, right? So what could give, I mean, so it looks like we are getting a contradiction. So if R is non-zero, then we have a contradiction. So we get a contradiction to the choice of F. If R is not equal to 0. But we cannot get a contradiction. So R equal to 0, which implies, looking back at this equation here, this equation, G is equal to QF, which implies G is in I. Sorry, G is in F. G was in I by hypothesis. So let me write this clearly. G is a multiple of F, and therefore it belongs to Z. So this is Q. Okay. What is important in this proof is that, you should pay attention to the little detail. I have chosen F to be non-zero here. I have chosen F to be of minimum possible degree and monic. So in fact, this shows, another thing that this shows is that, okay, note, this shows that the F of minimal possible degree, non-zero F of minimum possible degree and monic is unique, and monic in I, let me say. So in I is unique. Okay. So can somebody tell me why this is so? It follows from the proof.
Suppose two generator. Suppose it has two generators.
Yeah. Suppose this
One
has
should
two.
be,
Okay. So suppose F,
F1, F2, or 2.
F and F prime, let me call them, are two such polynomials. Okay.
Then F should be multiple of F dash, F prime.
Yeah. Then F should be a multiple of F dash. Very good.
Now apply the degree both sides. The degree of Q should be 0.
So the degree of Q should be
that is constant, should be constant.
Okay, degree of Q should be 0. Okay.
So Q should be constant.
So implies Q should be constant. Q is a non-zero constant. Okay.
Since F and F dash are monic polynomial, therefore the constant should be 1.
That implies and further implies Q equals 1 since F and F prime are monic. Indeed, that's correct. Thank you, Anomaly. Right. So this follows from the proof. It may not be immediately, it's clear, but you can easily prove this using this. right? So not only is this generator of minimal degree and monic anything that generates it, but it's actually unique. Okay.
Even you can add the step to why these minimal polynomials exist.
Okay, I didn't follow that anomaly. Could you expand?
What is the guarantee that the minimum degree polynomial exists in this set?
That is sort of the argument that suppose it is a non-zero polynomial, choose one, right? So it has some finite degree 10 or something. Right?
Yes, we can use the well-ordering principle also to choose this. If you collect all the degrees of the polynomial from this I, degree is always natural number, therefore well-ordering principle is the least element. Corresponding we have a least degree polynomial.
Right, you could say that very formally, but I didn't want to use. You are right, absolutely right. Right, you can say that formally that way. The point is, that part is, one would say, clear. Okay, even you can explain this to students and they will accept, who have not heard the well-ordering principle, and they will still accept this proof. You have some degree, say 10. If that's the least degree you have, fine. But if not, then maybe somebody has found a polynomial of degree 8 or something, then you choose that. And then you ask yourself, is that of the minimal degree, etc. Then, if not, then there is something else of lesser degree, and so on, right? But you cannot go on and on with this, because after 8, it may be 6, it may be 4, but at 1 you've got to stop, right? Or at least at degree 0 you've got to stop. If it's the entire ideal, then you'll have the identity element 1 there. Okay, so the point I want to make here also is that, see, so it's a formalization of mathematics is a tricky thing. It's sometimes we need to do it, but when you do that, it becomes, when you do formalization without adding content, then it becomes pedantic, right? So I would say do not layer it with formalization, except if it adds something new to it. Okay, right? Okay. Anyway, that's a aside. So thank you, Anomaly. That's thank you for dictating to me that proof. Okay. Now, so here is the point. Now let's get back to our right situation. So K is a field. V is our vector space, d-dimensional vector space over K, and T, V to V, is a linear transformation. Okay, and we have made V into a K mod. So you have made KT. So V is now a KT module. With T acting as T. Okay, what this means, you can say this in other words, you have a map KT to this ring, end of KV, right? So can I ask you a question? What's the dimension of this ring? It's actually a vector space over K, and it's a finite dimensional vector space. What's the dimension of that ring as a vector space over K?
D square.
D square. And why so?
That is dimension of V into dimension of V.
Correct. That's correct. D square is the right answer. in fact, it's isomorphic to this ring. And
K
this
D
ring,
square.
K. Right? D by D matrices over K. This is a ring, and it's isomorphic to this ring, right? That's what we said. And this is clearly D square dimensional, right? Over K as a vector space. So this is D square dimensional vector space over K. Okay. So this is a ring homomorphism. Okay. In particular, it's a vector space homomorphism as well. This respects the multiplication by K, the scalar multiplication by K. Okay. Now, what's the dimension of this ring as a vector space over K? KT. This is the polynomial ringing. Dimension. Of, yes, please say that again. I didn't hear it. Is equal to infinite. Very good. That's infinite dimensional because what's the base is 1t, t square, t cube, dot, 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 t to the 4, t to the 5, etc. Very good. Right. So that's infinite dimension. So what can you say about this map? Okay, one thing you can say immediately is that this is going to have a certain kernel, right? Non-zero kernel, right? Let K be the kernel of this map. K is and let me put it here, is an ideal because it's a ring homomorphism. There's a ring homomorphism and it's the kernel of a ring homomorphism. So it's going to be an ideal, two-sided ideal here, or just an ideal because this is a commutative ring. Okay. K is a non-zero. Is this clear? Because if K were 0, then this would mean it's an injection. And it would mean that you have a infinite dimensional vector space sitting inside injecting into a finite dimensional vector space. Right? That is not possible. So this kernel must be non-zero. In fact, it's a fairly large ideal. Well, I mean, is this okay? Now let me ask you a question. So this K has consider it's a non-zero ideal, right? Consider K, consider the unique minimal degree monic generator of K. Okay, our unique minimal degree monic element in K, element in this K, the kernel. So let's call it P. Okay. Now, can you tell me what this P is? You know this P. Right? What is P? I mean, the question is, can you identify this? As something that you know. From linear algebra. And it is attached to the linear transformation. Anybody, please?
Should be a characteristic polynomial of T. Or
No.
it should
No.
be degree should be D square minus 1.
Yeah. But degree should be no, it's not the characteristic polynomial. What is the characteristic polynomial degree of T?
So here we cannot define it.
No. Wait a second. T is a linear transformation, right? On a D-dimensional vector space. So it has a characteristic polynomial of degree
D.
D. Right. Characteristic polynomial of degree of T is of degree T. Okay. Now this P is not, I mean, is the kernel of, is the generator of the kernel of this map. Right? So for example, here, let's go back to this example. In this example, right? What is it? Can you identify the kernel? What is the kernel?
Should be the
Span of one.
multiples of X. Polynomial generated by X.
No.
Scalar.
Wait a second.
Scalar, constants. Constant polynomial.
That's in the kernel? Why is that in the kernel? If I act as a, no, what does it mean? So first of all, where does the kernel live? The kernel is an ideal inside this R adjoined T, right? So let me use this nomenclature. K, right, which is the kernel, lives in this. K is R here, so let me write it. It's R adjoined T. So it's a ideal in this PID. What do we mean? It consists of all polynomials, right? So if I take, say, for example, constant polynomial 2, it acts as just 2 on these polynomials in X of degree less than or equal to 3. So if I act that, say, 2 on X, I get 2 times X, which is non-zero, right? So the kernel consists of all those polynomials which, when I act on any element of this vector space, I must get 0. 2 is not such a polynomial because 2 acting on X is just 2X. 2 acting on 1 is just 2, which is not 0. So can you identify the kernel here?
T cubed.
T cubed, very good. Kernel is T cubed. Why is that, ma'am? Very good, beautiful answer. I'm happy somebody is getting it. Why is that?
That's the minimal polynomial.
That's the minimal polynomial, right? So, no. Can you say it in more fundamental terms? That's right. That's right. What you're saying is correct. Yeah. So, if I see any polynomial in RT, if it has some term which involves just t or t square, right? So it must act as 0 on even 1, right? So if the fact that it acts as, so this is in the kernel means it acts as 0 on everything. It acts, so let us check if it acts as 0 on 1. What all acts as 0 on 1? Well, if a polynomial has non-zero constant term, that will not act as 0 on 1. So the fact that any element of k acts as 0 on 1 means that elements of k do not have constant terms. They have 0 constant terms. Okay, now let's proceed. What polynomials act as non-zero on x? Right. If it has a constant term or t term, right? Just a t once, because the first derivative is non-zero, right? So if I have degree 2 or above, it's going to be 0 on x. Similarly, if it is going to be 3 or above, it is going to be, actually, it's not T3. Oh, sorry, I made a mistake. It's T4. Right. T3 also is non-zero because this x cube, you act theta, if I act 3 times, I'll get 6, right? First derivative is 3x squared. Second derivative is 6x. Third derivative is x. Right? So it's actually t to the 4. Okay. Now, what is the answer to this question here? What is this p?
Minimal polynomial degree of t.
It's the minimal polynomial of the linear transformation t.
Degree t.
No, you don't need to say degree. The minimal polynomial of the linear transformation t, you see, that's a fixed thing, whatever degree it has. Right? In this case, it happened to be degree 4, right? But it could be some other degree. Is this okay? So this is going to be the definition of my minimal polynomial. Okay, so I'm going to make this a definition. So definition. In fact, this is an answer because I'm relating it to something that you know, but what we are going to turn things around and say that this p is called the minimal polynomial. I'm going to make that the definition. See, after all, how do you define the minimal polynomial of t? It is monic of minimal degree that when I put t into it, that t satisfies. That's precisely what our definition is, right? The kernel is all polynomials, which when I put t in, I get 0. And then the monic element in the kernel of least degree is indeed this generator. Therefore, it is, that is proving that these two notions are the same. The one that you already know and the one that we have here. Okay. Right. Okay. So the next thing I want to do is do the Cayley-Hamilton theorem. And what does the Cayley-Hamilton theorem say? Can somebody please recall that for me from linear algebra?
Every matrix satisfies its characteristic polynomial.
Every matrix satisfies its characteristic polynomial. Okay, very good. That's indeed correct. Okay, so let me write it here, but let me write it in lighter black. So every matrix, every square matrix, or let me say D by D matrix, satisfies its characteristic polynomial. Very good. That's the, okay. Now, but let us state it in this language. So in our language, what would it mean? What would, instead of satisfies, what would it mean? When do you say something satisfies? When does a matrix satisfy a polynomial? So, what
Annihilates.
is that?
So annihilates it.
Correct. But in terms of this, in terms of the language we have developed, what would you say? Where
Every linear transformation on a finite dimensional vector space annihilates its characteristic polynomial.
No, that is, see, you're not, that's correct, Annamalai. I'm not denying that. But in terms of what we have used, in terms of this language, what are we saying? Okay, let me tell you, and then it's saying that the in our language it is the characteristic polynomial of T belongs to the kernel K, this idea. So this is this kernel. This was by definition the kernel from KT to I mean either MD K T acts like the matrix with respect to some basis. Okay. No, all I'm saying is, this satisfies, we have turned it into belongs to K. Okay. Now, what does this mean? When does something belong to K? What is the generator of K? We've called it P, right? And that generator we have called the minimal polynomial. So, in other words, what can you say? How can you say this? In other words, this is the minimal polynomial P
Divides the characteristic polynomial.
Divides the characteristic polynomial. So of T, of course, and of the same transformation. Okay. Let me quickly ask you, we are almost out of time. Do you know proof of this theorem? The statement is simple enough. Do you know a proof? Okay. Let me say next time, in the next lecture, that is on, I guess, Sunday next week, we'll prove the Cayley-Hamilton theorem using the determinant trick. This is a very useful and beautiful idea in ring theory. And it is explained, for example, in the second chapter of this book. It's explained in several places, but in particular, it's explained in the second chapter of this book, Atayam et al., which Professor Vijay is following. I understand that he's still covering material from the first chapter, right? So what we will do is that we will prove the theorems of linear algebra relate them to the ring theory theorems and derive them as special cases of these theorems in ring theory, where how the ring theory comes in is precisely through this. V has been made into a KT module. And this is the basic idea. We will exploit this idea and the theorems of ring theory to derive the main theorems of linear algebra. So the first thing in that theme is that we are going to prove the Kelly-Hamilton theorem using the determinant trick. Okay, I think I'm already over time, so let me stop here. Thank you for your attention, but if you have questions, I'm most happy to answer them. Are there any questions?
So no questions from.
No questions. Okay, how many participants do we have? See, it becomes, I guess all of you are also teachers, and you know, all of us are reduced to doing these things online. Online has its advantages. I'm not complaining, but one of the things, one of the disadvantages is that I have no idea, you know, if any of you, you know, I can't make out. I can't even make out whether you're there or whether you're just have your machine on and doing something else. I can't say, I have no idea. And so some feedback would be good for me to ensure that whether what I'm doing is making sense or making no sense. So, right, this program, we don't have to cover any material. We are not in a rush to cover the syllabus or anything like that. Right, we are just trying to understand some very basic material. So it would help if you know, it would help me immensely if you interact and give me feedback. Right, without that, I'll be lost. Right, and so I hope you understand what I'm saying.
So today only the attendance around is 60, sir. But in the last sessions around is 73, 75.
Oh, I see. Okay.
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 Maybe
Okay.
Sunday.
Okay. 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 No problem. I mean, it's okay with me. I mean, and maybe they are on YouTube, right? You don't get to see those on YouTube, right?
Yes, sir.
Yeah. Okay. Anyway, so have you know, a good week ahead, a pleasant evening, and a good week ahead. And I will see you on Sunday next week. But of course, there are Professor Vijay is going to continue his lectures on Thursday and Saturday, according to the schedule. So thank you so much. And I'm going to, Gurusamy, I'm going to send you the PDF file right away.
Okay, sir.
Of the notes.
Sure, sir.
So you can please feel free to share it with them. Please share it with all the participants.
Sure,
Okay,
sir.
sir.
Okay.
Thank you, sir.
Thank you. Thank you.
Thank you, sir. Thank you, sir.
Thank you so much,
Thank
sir.
you for your nice lecture, sir.